Okay, in this video, we're going to be looking at proving the value of this special limit, the limit as theta approaches 0 of sine of theta over theta, and we're going to use sandwich theorem to prove the value of that limit. Okay, so we're going to use some trigonometry, some sandwich theorem, a little geometry, some algebraic relationships, so this is a pretty fun proof. There's all kinds of stuff going on in this proof. Okay, so here we have a diagram of just a generic angle theta labeled here in the first quadrant. So this picture would be a picture of a theta that is bigger than 0. So we can see that this angle is larger than 0 radians or 0 degrees. All right, so it might look like a specific angle, like about a 45-degree angle, but this is intended to represent a generic angle theta, and remembering that we're going to let that angle approach 0, so we want to let that angle get smaller and smaller anyway. So for this part, we're really going to be looking at, since theta is bigger than 0, we're really going to be looking at, for this part, the limit as theta approaches 0 from the right, since we have theta values that are bigger than 0. Okay, so to start with, though, we're going to look at this diagram here, and we're going to remember that this, we have a unit circle here, and we can tell it's a unit circle because we can see that the radius here is 1. And so we're going to label the coordinates of this point that's labeled P. So if you remember back to your trig and think about how sine theta and cosine theta are defined in terms of the unit circle, the coordinates of this point here would be cosine theta for the x-coordinate and sine theta for the y-coordinate. So I'm going to kind of just label that here on the diagram. So this side here, this distance here would be sine theta. Some people tend to think about their trig functions in terms of triangles. So putting this little triangle in here maybe would help those people. And then the x-coordinate of that point would be the cosine, the theta. And since it's a unit circle, remember that that radius would be 1. Okay, so I'm going to just kind of darken in those sides of that triangle. We're going to use those to do some other stuff here in a little bit. So we've got one side labeled sine theta and the other side labeled cosine theta. Okay, so what we're going to do is use that and some other triangles and relationships to get some sandwiching here. I told you that we're going to use sandwich theorem. That's kind of the clever thing for this proof. So here I have 3 different diagrams. They're all really the same diagram. I'm just kind of emphasizing different parts of them. So the first one here is that same one that we just looked at. Cosine theta is the length of that red side in the x direction, and sine theta is that blue side, the y direction on this triangle. And what we want to do in this first diagram is write down the area of the triangle. I'm going to use some geometry notation here. Triangle OAP. So there's a lot of points here labeled, but if we're going to find the area of triangle OAP, we're looking at this whole triangle here. We want to find the area of that triangle. So you might remember that the area of a triangle is 1/2 times base times height. And so we want to look at that whole triangle that I outlined there in black, OAP. So since it's a unit circle, that cosine theta, remember, is just the red part, but since it's a unit circle, we know that this distance from the origin to point A is 1 unit, so that's our base. And then the height of the triangle would be that blue side. So that's the sine theta. So the area of this triangle is 1/2 times 1 times sine theta, or just 1/2 sine theta. Okay, so for this second triangle here, I've just taken the same unit circle that we started with, and I extended this line that was through O and P all the way out to form this other point T. And I've got a perpendicular side here kind of labeled in gold, and we want to represent this triangle. We want to represent the area of that triangle, OAT. Okay, so again, we can use the formula for area, 1/2 base times height, and the base of that triangle is this side, which is 1. But there's a question mark labeled on another side, which we're going to need to figure out before we can write down the area of this triangle. So in order to think about the length of this side that is yellow and has a question mark labeling it, There are a couple different ways we can do that, but maybe the easiest way to do that is to use those Sohcahtoa relationships that you might remember from trig. So if I look at my angle theta, then this side that has the question mark is the opposite side of that right triangle, and I know the adjacent side. The adjacent side is 1. All right, so I could say that tangent theta is opposite, that's my question mark side that I'm trying to figure out, over 1, over adjacent. Tangent is opposite over adjacent. So that question mark side, if I simplify that, you get that the question mark is equal to tangent theta. All right, so the area of this triangle is 1/2. The base is 1 across the bottom. That's the adjacent side. And then the height of this triangle, OAT, the height is that gold side, and so that's tangent theta. So 1/2 tangent theta. Okay, the last picture is the same diagram that we started with, but what I have shaded in here is what's called a circular sector. And in trigonometry or pre-calculus, you should have done some area of circular sectors. Students tend to not remember this formula very well, so I'm just going to go ahead and write this down and talk about it a little bit. The area of a circular sector is 1/2 r squared, where r is the radius, times the theta, and that formula only works if theta is in radians. Okay, so from here on out, we're going to need to assume that the theta in our problem is given in radians. And of course, if it were in degrees, we could just convert it to radians. We know how to do that. Okay, so the area of this circular sector here, of circular sector OAP, is going to be 1/2. The radius is 1. And our theta is what's labeled there in the picture. So 1/2 theta. All right, so the next thing that we want to do is look at these three areas of these three regions. I've got the triangle OAP in the first diagram. I've got the triangle OAT in the second diagram, and then the circular sector that's already shaded there in the third diagram. And if I look at those and compare those areas, you should be able to put those areas in order from smallest to largest. Right? So the area of the first triangle, OAP, is going to be the smallest. So 1/2 sine theta is going to be less than the area of the circular sector, which is 1/2 theta. And that will be smaller than the area of the middle picture, the triangle OAT, and that area is 1/2 tangent theta. Okay, so what we have right here should start to make you think about sandwich theorem. I've got a sandwich. All right, so the question is, it's not really the sandwich we need in order to prove the limit that we were after. So we're going to do some algebra on this and get it to look like the sandwich we actually need. We just have to be careful to make sure we don't mess up the inequalities. All right, so the first thing that we can do here is multiply through this inequality by 2. If I'm multiplying through by a positive number, that doesn't change the direction of the inequalities. So I'll have sine theta is less than theta is less than tangent theta. So what I really want is, I want to look at the original limit. Let me just scroll up so we can look at that. Theta approaches 0 of sine theta over theta. Okay, so there's a couple ways I can get that, but that's the expression I really want in the middle here, sine theta over theta. Okay, so I'm going to start here by dividing through by sine theta. Since our angle theta was in quadrant 1, sine theta will be positive, and so I'm dividing through by a positive number, so that's not going to change anything with the inequalities here. So I'm going to divide through by sine theta, or think about multiplying through by 1 over sine theta. And since theta is not equal to 0, I don't have to worry about this sine theta being 0. Okay, so when I multiply through by 1 over sine theta, I get 1 is less than theta over sine theta. And then on the right end, if you remember that tangent theta is sine theta over cosine theta, the sine thetas will cancel, and I'll be left with 1 over cosine theta. And all of those expressions will be greater than 0 because our angle here is in quadrant 1, theta is bigger than 0. Okay, so I'm getting closer. I have a sandwich that almost looks like what I want here. So the next step would be to take reciprocals of these inequalities. And remembering that we have positive numbers, if you think about positive numbers and you remember how they work when you do inequalities, if you just think about an example, 2 is less than 3, those are positive numbers. If I take reciprocals of both of those, though, and I think about how that inequality works, then really 1/2 is bigger than 1/3. So as long as everything's positive, when I take reciprocals, the inequality flips when I do that. Okay, so the next thing that I'm going to do here is take reciprocals of everything, and that will flip those inequalities, and it will give me the sandwiching functions that I wanted. So the reciprocal of 1 over cosine theta is just cosine theta. Okay, so the point of sandwich theorem is that you take a function that is perhaps a little bit difficult to work with. That's the function we started with that we want to figure out the limit of. You sandwich that function between two functions that are easier to work with. Okay, so cosine theta and 1 are both easy functions to work with. So I'm not quite done yet. What I need to show is that the cosine theta and the 1 both approach the same thing as theta approaches 0. All right, so the limit as theta approaches 0 of 1 is just 1. That stays just 1. So that limit is 1. And then on the other end, the limit as theta approaches 0 of cosine theta. So that's a trig function. It's well behaved and well defined everywhere around theta equals 0. So we can use a substitution shortcut theorem for that. So the limit as theta approaches 0 of cosine theta is also 1. All right, so then sandwich theorem says that if I have this sandwiching relationship, the inequalities, and the limits of the two functions on the ends are the same as theta approaches that value, then we can conclude that that limit that we were really after, that we wanted in the middle, is the same, is pinched to the same place as those other two limits. So we can then conclude that the limit as theta approaches 0 of sine of theta over theta is also going to be 1. And that's what we were really after. Now, you might remember that at the beginning, we started with an angle theta that was in the first quadrant, so our theta was bigger than 0. So technically, all we've really shown so far is that as theta approaches 0 from the right, that this limit, the limit as theta approaches 0 from the right of sine theta over theta is 1. So that's really what we've shown. In order to complete the proof, we really need to show that it's the same when theta is less than 0, or when theta approaches 0 from the left. So there are a couple ways we can do that. I'm not going to go through all of the details of that, but you see here at the screen now, we've got a theta value that is less than 0. This angle is in the fourth quadrant here. That theta is less than 0. So this picture could be used to show the limit as theta approaches 0 from the left of sine theta over theta is also 1. So you basically do the same thing. You create a sandwich, a relationship. You have to be a little bit careful about the inequalities because sine theta and theta will both be negative in that quadrant. So you have to be a little careful with the inequalities. But you can also show that this limit is 1. Then you can use the theorem about two-sided limits. And so we know that the limit as theta approaches 0 from the right of sine theta over theta is 1. And we can show, I didn't do it, but you can do the same argument and show that this limit is also 1. And so we have a theorem about two-sided limits that says if the two one-sided limits are the same, then those two limits tell us that the overall limit will be the same, will also be 1. All right, so there we've proven what we set out to prove. You could also check on your calculator that that makes sense. Remember to be in radian mode for that. So this is always important that theta is in radians. All right, and once you've proven that this limit is 1, this is one that you should eventually memorize. So by the time we get to an exam, you want to make sure that you have this special limit memorized. You should also probably understand that you could prove it using sandwich theorem. I won't necessarily ask you to recreate this entire proof, but you should understand that it's really sandwich theorem and some trig that gets you to this limit.